Hello everyone, my name is Vivya Krishna, rule number 20951A2130, branch Aeronautical Engineering, subject finite element analysis. So today here I am going to discuss about convergence requirements of structural analysis. Here we want to know about FEA element types. That is, elements fall into four major categories. That is 2D line elements, 2D planar elements, and 3D solid elements, which are used to define geometry. Special elements used to apply boundary conditions. For example, special elements might include gap elements to specify a gap between two pieces of geometry. Spring elements are used to apply a specific spring constant at a specific node or set of nodes. Rigid elements are used to define a rigid connection to or in a model. Truss element, that is 2D line. The truss elements are long and slender, have two nodes, and can be oriented anywhere in 3D space. Truss elements transmit force axially only and are 3 DOF elements which allow translation only and not rotation. Here in the figure we can see the 2D line. Coming to beam element, that is also 2D line. The beam elements are long and slender, have two nodes, and can be oriented anywhere in 3D space. Beam elements are 6 DOF elements, allowing both the translation and rotation at each end node. 2D element, that is the planar, 2D planar. 2D elements are 3 or 4 node elements with only 2 DOF Y and Z translation and are normally created in the YZ plane. They are used for plane stress or plane strain analysis. Coming to plane stress, plane stress typically occurs in a thin flat plates that are acted upon only by load forces that are parallel to each other. Implies no stress normal to the cross section defined. Strain is allowed, suitable to model the 2D cross section of the wall subject to axial load. Here we can see the thin flat plate and the stresses. Stress sigma equal to sigma 11, sigma 12, 0, sigma 21, sigma 22, 0, 0, 0, 0. That is 3 cross 3 matrix. And the corresponding strain tensor is sigma ij equal to sigma 11, sigma 12, 0, sigma 21, sigma 22, 0, 0, 0, sigma 33. This is about the plane stress. Coming to plane strain, implies to no strain normal to the cross section defined. Stress is allowed suitable to model the 2D cross section of the long dam. Here we can see the formula of the stress and strain according to plane strain. This is the figure of plane stress and plane strain. According to plane strain, that is a thin body, and according to plane strain, it is a thick body. Sigma z equals 0 and epsilon z equals 0 in the plane strain. Membrane element 2D planar. Membrane elements are 3 or 4 node 2D elements that can be oriented anywhere in 3D space. They can be used to model thin membrane like thin metal cells, etc. These elements support only translation DOF, not rotational and in plane loading. The thickness of the membrane must be small relative to its length of or width. Plate element 2D planar. Plate elements are 3 or 4 node 2D planar elements that can be oriented anywhere in 3D space. They are typically used to model structures cells comprised of cells such as pressure vessels. Generally a thicker wall than for a membrane element but about 1 by 10th the length or width. All translational DOF are supported as well as rotational DOF that are not out of plane. Coming to 3D brick element, it has 8 nodes. It is 3D solid. Brick or tetrahedra elements may have 4, 5, 6, 7, 8, 15 or 20 nodes and support only translational DOF. They are normally used to model solid objects for for which plate elements are not appropriate. You can usually specify either all tetrahedra, all bricks, or a mixture of both with some automatic mesh generators. Coming to requirements for conversion of the solution, the finite element approximation must satisfy certain conditions which guarantee that as the mesh is refined, the numerical solution converges to exact values. The continuity condition. The displacement must be continuous within each element. This condition is automatically satisfied by using polynomial approximations for the displacement field. Rigid body condition. The displacement held closed should not allow straining of an element to occur when the nodal displacements are caused by a rigid body motion. This physical condition is satisfied for a single element if the sum of the shape functions at any point is equal to 1. Constant strain condition. The displacement function has to be such that if nodal displacements are compatible with a constant strain field, such constant strain will will be in fact be obtained. Clearly, as elements get smaller, nearly constant strain conditions will prevail in them. The computer code trust.m. The MATLAB is a high level language specifically designed for dealing with matrices. This makes it particularly suited for programming the finite element method. In addition, MATLAB will also allow the reader to focus on the finite element method rather than on the programming details. Programming the finite element methods involves the following steps. Step 1, data preparation and input. Step 2, computation of element matrices. Step 3, assembly of elements, stiffness matrices and elements force vectors in the global stiffness matrix and global force vector. Step 4, imposition of boundary conditions such as prescribed displacements. This is usually carried out simultaneously with the assembly of the global matrix in step 3. Step 5, solution of the global system of equations for the nodal unknowns. Step 6, computation of secondary variables such as stresses and strains from displacements. Step 7, print and or plot desired results. The FE meshing. The idea is that we are going to use a simple approximation method, but the errors in this approximation method become unnoticeable as the size of the surge subregion gets small. Here I have given a figure of meshing. The mesh must be able to adapt the local features in this 3D case or curvature. Thank you. This is all about the convergence requirements of a structural analysis. Thank you.